Hello, here's promised example of induction. Done in the simplest variant, and the example is summing arithmetic progression. The simplest, again, situation of this arithmetic progression is starting with 1, sum up all the numbers up to a certain number n. So that is the task, to find a more or less compact expression better than the sum for this result. Well, let's assume that we don't know the answer. Let's do what people usually do in these situations: experiment. So when n is equal to 1, the sum is just 1. Well, there's not much to it. Let's look at the next in line. This is a sequence of statement going to be, when we will figure out the right hand side, labeled by the number of summons. So now we have 2 summons, and we can just add 2 to 1, and we get 3. And maybe I should just draw the pictorial shape of what is going on. So here we have just say one standard box. Here we have the sum of 1 box and the 2 boxes, and I will be drawing the summons vertically. And then I can look at the next in line, so we can quickly compute the sum by taking the previous answer and adding the last term to it. Right? So that will be 6. Pictorially I have the previously drawn picture, and then I attach to it another line now of length 3. Let me try the next one. I have 1, 2, 3 and 4 to be summed, and that is just 6, the previous sum plus 4, which is 10. So have to reproduce the original, the previous picture, and then extend it by one more line of length 4. Geometrically, geometry is always a great help. Geometrically, if you imagine the number of summons growing, so what will it look like when the number of summons will be really large? So this is arbitrary n case. Here you have, look, the sides of these 2 sides are length n, always of the same length: 2, 2, 3, 3, 4, 4, and so on. So this will be length n, this will be length n. The picture will be inside the n square, square of length n, of side n. And then if you're really looking at the large n, you will not see well the diagonal. It will be blurred into a line, and then the upper half will be your shape. So for large n, this sum looks approximately like half of the square. So this is the symbol for approximate, and this is the formula for the number of standard squares inside the square of size n. So that is a hint. What is going to happen is probably less axiomatic, less hard to put into a framework, but this is a hint. So we know that approximately our sum is product defined with itself halved. So let's try and see how really it works. It cannot work precisely because, well, not all squares are even, so we can't even divide sometimes by 2, but we always have to have an integer answer, a natural number answer. But let's try to do sort of the best, next best thing. Well, fix the denominator to what it should be, and then, well, try to see one copy of n inside n square. So here n is 2. Well, I should start in here, and then I'll just have 2, and it's not much in a sense, but I can write 2 as 1 times 2, but you'll see why. So this is not 12, this is 1 times 2. Here I have to see still 2 in the denominator, and then the number of summons n is 2, so I will write 2 again, and then I have to write 3 here, nothing else. Here again, if I start with the denominator 2, put upstairs in the numerator the number of summons, the remaining thing is possible again, and it is 4. So that in total will give me my true answer 6. Again, imitating, putting 2 in the denominator, putting the number of summons and trying to imagine a thing here, and the thing is unambiguously 5. And here we have a sequence of repeating statements. So all the time we have the denominator 2, we have n as a first factor of the numerator, and the second factor of the numerator is for n being 1 is 2, for n being 2 is 3, for n being 3 is 4, and for n being 4 is 5. Well, it's the next in line, it's n plus 1. So this is, at this stage, is just an experimental fact checked for the first 4. Let's prove it. That is to be proved still. Let's prove it by induction. Now this is our statement. It's our conjecture right now, but let's make it a statement number n, that the sum of first n numbers is possible to write as the product of the number n and the next, and then halved. And to run the induction, we have to start with the base. The first statement is when n is equal to 1. The left-hand side is 1, the right-hand side is 1. 1 plus 1 over 2, which is 1, so we have the base checked. Let me separate my experimental part. Here will be the true mathematics proof part. Now I have to make an induction step. And I will do it in a simple version, so there will be a simple induction step, assuming statement number n, that the sum of the first n natural numbers is equal to n plus 1 multiplied and then halved. Assuming I need to see that the sum of the first n plus 1, so I will write it as such first. It should be equal to the answer, but modified for the case where my summons are n plus 1, stopping at n plus 1. So all the instances of n should be replaced by n plus 1. So there it should be n plus 1, and then n plus 1 instead of n plus 1, all halved. So before proceeding, I'll just simplify it into what it is, n plus 1, and here it is nothing but n plus 2, all halved. So that's what I should see as this sum. And this sum, again, is sum of the first n plus 1 natural numbers. Inside it, I could see the sum of the first n natural numbers, and then on top of them, I have the next one, n plus 1. And by assumption, this sum, here's my assumption, this sum is equal to n times n plus 1 halved. On top, I should have n plus 1. Now let's compare the terms. So what can we do with this to match with that side, to compare with that side? We can make a common denominator. So when we make a common denominator, we will have n plus 1 times 2 in the common numerator. And n plus 1 times 2 combined with this will give us n plus 1, factoring out, and the remaining will be n and 2 from here. So that will be just making n plus 2. Let me spell it out. So here I'm making a common denominator by simply, that is n plus 1, but simply multiply n plus 1 by 2, and then factoring n plus 1 out of the numerator, I will have n plus 1, and the remaining sum will be 2 and n. So that's what I have. That's what I have. That's what I wanted to have. That is the checking point of the step. So the step is done. So we proved this formula for summing an arithmetic progression. Prove it by induction. See you later.